All right, let's go and review some things we talked about in our last lesson. We began looking at our final state of matter, at least the final state of matter we will study in any depth. And of course, Michael, that is the solid state. And what makes the solid state unique from the other two, Audrey, is that it has, or that solids have, definite shape. Thank you. Sorry, definite shape, meaning they don't flow. They're not fluids. And so we said that solids have a definite shape up to a point. And we gave the example in our last lesson that, for instance, this calculator has a definite shape until it doesn't, right? What will we call the change of shape of a solid caused by some external force? What do we call that change of shape? Mangling would be a practical term. What's the more scientific term for mangling or breaking or smushing? Do you remember that term we used a lot yesterday? Deforming, right? Is that idea of changing the shape of a solid, but again, it requires some external force. And yesterday we said that in general, the reason solids have a definite shape is because all solids have some tendency to maintain their shape. Some have a very high degree of maintaining shape, and some can be relatively easily deformed. Play-Doh, for instance, right? Very easily deformed. And so we said in general, the term that describes the ability of a solid to maintain its shape, we call this more general term. Elasticity. Elasticity in general is maintaining shape. Now there's two ways to maintain shape. One way to maintain shape is you just don't get deformed in the first place. And that's rigidity. The tendency to resist deformation is rigidity. Other things like rubber bands easily get deformed, but they recover their original shape after being deformed, right? Pull on the rubber band, it deforms, I let go. You would have never known that I pulled on the rubber band, right? Because it looks the same as it did before, right? We call this ability to recover original shape after deformation.
Elasticity.
Well, it's a part of elasticity. It's one of the two aspects of elasticity. Resilience, bouncing back after being deformed, right? Recovering original shape is resilience. So, in general, maintaining shape is called elasticity. Elasticity, maintaining shape by not getting deformed is, and maintaining shape by recovering shape after deformation, resilience. There we go. We said the ability of a solid to be permanently deformed is that of solids' plasticity. Ability to be permanently deformed, plasticity. We said metals in their natural state are very rigid, most of them. Lead, not so much. But metals tend to be very rigid. But if heated, you can work with metals. And we talked about 3 metalworking processes. Michael, do you remember what those 3 were?
Forging, drawing, and rolling.
Forging, drawing, rolling. Which one involves making metal into a continuous sheet, a long continuous sheet? Class? Rolling. And we simply would use heavy rollers to force the metal between the rollers and comes out to a nice continuous sheet. We said which one involves using a 2-sided die oftentimes and squeezing or pounding the metal between the die till it hardens into a solid shape. Forging. Do you remember the other name for forging?
Casting.
Casting. And then the last one, forcing the metal through a single cut die and producing a long wire is called drawing. And what is the property of a metal that allows it to be rolled or hammered in the old days into sheets? Malleability. And then the property of metals that allow some of them to be drawn into long wires? Ductility. All of that was kind of that first section, 5.1. Then we went into section 5.2, and we talked about stretching things. You know, I've got a meter stick up here. If we're to grab on the meter stick and pull in opposite directions really hard, nothing really changes. But the force that was being applied to try to stretch out the meter stick, or the force that's applied to stretch a rubber band, or the force that's applied to stretch out a spring, that stretching force, well, that's how we would describe it in plain English, but of course scientists like to make things sound cool. What's that sciencey word for stretching force, Michael?
Tensile.
Tensile force. tensile force, spelled tensile, we just pronounce it tensile. Not tinsel, that's what goes on the Christmas tree in about 3 months. Tensile force. And we said that as I pull on the spring right now, there is a tensile force that is built up. Right? I'm applying a tensile force. It's pulling against me. You know how I know it's pulling against me? Because, well, for one thing, I can feel it. You know how you know? Because when I let go, it pops back up, right? And Kendall just woke up. Right? It pops back up, right? There's a force pulling against me so that when I let go, it pulls the other direction, right? And so we shot Michael yesterday with a rubber band. Really, I just pulled on the rubber band, and the restorative force caused the rubber band to propel itself forward. Was it not I? What's going to be true about tensile force and restorative force in any given situation? Unless, of course, the rubber band breaks, which this is kind of a skinny one, so I don't think I want to break it. It might break anyway today. We'll find out. But what would be true unless there's breakage about tensile and restorative force, Michael?
They're inversely related or directly?
Proportional.
They're equal, but in opposite directions. So they are inverses. Not inversely related, but they are inverses of each other. So if I pull with a force of, let's just use US customary units, I pull with a force of, say, 5 pounds, it pulls back up with a force of 5 pounds. If I pull with a force of 3 newtons, it pulls with a force of 3 newtons the other direction. Okay? So they're inverses of each other. Now, both tensile force and restorative force are going to be proportional to something. The more force I apply, what happens? If I apply a little force, what happens?
A little force pulls back.
A little force pulls back. What happens visibly? I pull with a little force, stretches. I pull with a lot of force, what happens?
Much stretches.
Much more stretch. The amount of stretch is proportional to the force that's applied. Now, in this case, is pretty rigid, right? It's not getting deformed easily. Now I can break it this way. That's a different type of force. But tensile force, that stretching force, it resists deformation pretty strongly. But it's still going to be proportional to the amount of force that's applied. And we call that property Hooke's law. Now, Hooke's law gave us 2 equations yesterday. Michael, do you remember one of them?
F equals kx.
F sub t equals kx. F sub t meaning force of tension, or the tensile force, is equal to some proportionality constant, and for every object it's different. Every one of those things that are hanging up there have a different proportionality constant. And then the amount of stretch. The other equation is basically the same thing, Audrey.
F sub r equals negative kx.
Yeah, it just has the negative. And what does a negative show in physics, Michael? Not an inverse relationship. It shows an inverseness, but it shows a change in or opposite direction. There we go. The negative here, Kendall, just shows it's in the opposite direction. So we didn't get to actually do any of these tests yesterday, so I wanted to do them now. And that is actually finding these spring constants. So I've got up here a pretty thick rubber band. I've got a very thin rubber band. I've got an incredibly thin spring. I've got a thicker spring, kind of medium, and I've got a very thick spring. So a little of each of these. And what we want to do is we want to calculate the spring constant for each. Well, let's just take Hooke's law in its base form, tensile force equals kx. If I wanted to find the spring constant k, what would I have to do, Kendall? How do I get k by itself?
Divide away x.
Yeah, absolutely, divide away x to get k equals.
F sub t over x.
There we go, f sub t over x. Now for these, instead of pulling sideways, I've got them hanging so that whatever we hang, the force that is pulling on it is the weight of whatever object hangs. Does that make sense? So if I put, for instance, this object here, however much this gray thing weighs, that's how much force is pulling, correct? How do we find weight, or how do we even define weight? What is weight? The pull of gravity on an object's mass, right? So weight is literally equal to the mass of an object times the pull of gravity or the acceleration of gravity. So the tensile force here is just going to be mass times gravity. For instance, this here is a 500 gram mass. Well, I don't want grams, I want kilograms, which is an E3. So I need to move the decimal. And we'll say that instead of 500 grams, this is
0.5.
0.5 kilograms. Okay, so we have a 0.5 kilogram mass, and then G class we'll assume to be 9.80 meters per second squared. Again, is that exactly what G is in this spot in this lab? Probably not exactly 9.8, but it's close. In fact, we've got a scale. Miss Morrison and I tested it one day after school. I believe in the lab it's 9.806. So I think technically we'd round to 9.81, but since I'm only going off my feeble memory from a year ago, let's just stick with the 9.8 we're used to. Our results should be fairly consistent even regardless. So how much weight is actually pulling, how much tensile force is on that spring right now, class? 4.9 newtons of tensile force. And we can measure the stretch by measuring where this red marker starts out before we stretch it. Okay, so before we stretch it, this red marker, and I'll show it to you, but I'm going to have to see it myself. The red marker appears to be at 22.7 centimeters. So it's starting at 22.7 centimeters, and then we put the weight on it. It's going to stretch it down further so that the red mark lines up with, say, 40.4 centimeters. Now, there's the chance that the ruler is not perfectly vertical. And if it's slightly off, that's going to mess with the math a little bit. But we're not trying to break any new ground here necessarily. I think it's accurate enough. 40.4 centimeters to the stretch point. What is X then? If it goes from a 22.7 mark to a 40.4 mark, what is the stretch in the spring?
17.7.
Yeah, total is 17.7 centimeters, but for the stretch, because newtons involves meters, I'm going to need the stretch to be in meters. So let's change that to meters.
0.177.
All right, go ahead and divide, and let's get the K for my fixed spring. And what do we get?
27.683.
27.68. I'm going to round to 27.7 because I don't want to use values more exact than what we were using. Now notice the units here. 27.7 newtons per meter. That's my spring constant. Tell you what, if you would all write that down on your paper, the fixed spring, 27.7 newtons per meter. So we're going to get all 5 spring constants, if y'all will write them down. All right. Now let's go to another, let's do a rubber band next. We'll kind of alternate here. I don't trust this rubber band. It's very thin, so I'm going to go a little bit lighter. I'm going to put 50. That doesn't actually stretch much at all. That's a little too light. Let's go with 100. I could easily handle 100 then. No, I think we go 200. I want to do the 500. I'm not going to. Okay, there we go. Okay, so that'll hold it. All right, so what I'm going to do is I'm going to pull on it with an attempt to just straighten it as opposed to stretch it. Okay, because right now, see how it's not actually pulled taut? I think right there is pulled taut without stretching. And let me flip this the correct way. Pulled taut without stretching. I've got it sitting at 39.3 centimeters. 39.3 centimeters. I'm going to put this weight on here. It'll stretch it out so that the bottom seems to be, say, 50.5. All right, what's the stretch? 11.2 centimeters. Of course, we're going to change that and make it 0.112 meters. Now, this is a 200 gram mass, so it's 0.2 kilograms times 9.80 meters per second squared. How much force, tensile force, is stretching the rubber band, class?
1.96
newtons. All right, so what's the spring constant for the green rubber band?
17.5 newtons.
17.5?
Yes.
Mm-hmm.
Newtons.
And that came out evenly, or that's rounded 3?
Even.
Well, okay, write that down for the green rubber band. Now let me go to my little tiny spring here. And I may need to slide these down actually just a little bit. Make sure I'm not running into the sink. Okay, so let me go and get the standard spot for this spring. And it appears to be sitting at 20.3, if you write that number down, 20.3 centimeters. Whoa, this thing stretches a lot. Okay, I mean, it's a small spring constant. It's because it's a very lightweight spring. And it's kind of oscillating a little bit here, but looks like, let's say 50.7. 50.7. So what's our X?
30.4.
30.4, so let's say 0.304 meters. And once again, it's the 1.96 Newton weight, or the 0.2 kilogram mass. What's the spring constant for the lightest spring?
0.064.
Really?
7, yeah.
0.06?
I did 30.4. 6.417.
We like 6.47? Okay, so write that down for the lightest spring, 6.47 newtons per meter squared. All right, let's go with the thicker rubber band now. I think we'll just stick with the 200 gram mass. It's working well for us. Plus, that means I don't have to change numbers on the board. And yes, I am that lazy. All right. So we line this up, just pull it taut without stretching. Let's say 32.8. And that's not going down very much further. Wow. All right, 32.8 to 35.8. Wow, that's only 3 centimeters, or 0.3 meters. Or excuse me, 0.03 meters. Yeah, 0.03 meters. All right, what's the K? 3 centimeters, 0.03 meters. Yes, what's the K? 65.3 newtons per meter squared. You see a much higher K value, much higher constant proportionality for this than the green rubber band by far, right? So tan rubber band, get that number down. All right, and then we'll go to our medium spring. So what was our thick spring again?
27.7.
27, and what was the light spring? 17?
No. 6.47.
6, okay, so somewhere between those, give me a guesstimate, somewhere in the middle.
17.3.
17-ish? Okay, so let's just see, we're guesstimating, okay, based on how the other ones went, we're expecting somewhere around the 17 mark here. Go write down this number if you would. Looks like we're at 21.5. And let's say we're now at 35.5. 14 centimeter stretch. All right, so 0.14 meters, and it's the same mass. All right, what's the spring constant for the medium spring?
14.
Yeah.
14 exactly. Wow. Okay. So based on our calculations, and again, how exact are our calculations? Not very. Okay. Again, they're based on a rough guesstimate of where one thing ended up. Okay, so not super scientific, but I think our results will come back pretty accurate, because once you know the spring constant, you can calculate the stretch you would expect as you change the force acting on different objects. Let's go back to our heavy-duty spring.
We used 500 here.
We used 500 last time. Let me go with 300, okay? So jot down the starting position is 22.5. Actually, we're not measuring, we're calculating. Sorry, never mind. We don't need to write that. Well, it's okay to write that down. All right, so we know the spring constant, right? We said for the thick spring, the spring constant is that the 27.7? Newtons per meter. And we're going to put a force of, we're putting a mass of 300 grams. So at your seats real quick, 0.3 times 9.8. How much force is being applied?
2.94.
2.94 newtons, okay? I want to see how much should be expected to stretch. how much should we expect it to stretch? So how do we get the x by itself?
Divide K.
Now divide the k, which we've already calculated based on a prior test. 2.94 divided by 27.7. How much should we expect it to stretch?
0.106.
0.106 meters, which would be 10.6 centimeters. All right, so right now, you already wrote down the starting spot. Let me give you the ending spot. Looks like I'm at 32.6. 32.6. What was the starting number?
22.5.
32.6, and you said it was what?
22.5.
All right, so what's the actual stretch that took place?
10.1.
10.1. Okay, so we're about a half a centimeter off on our math. Again, there's a lot of reasons that those factors could be off, but about a half centimeter off. We were pretty close. All right, let's go to our green rubber band.
17.5.
All right, so 17.5 is our spring constant. Oops, that's actually stronger than the medium spring, isn't it? Slightly, because that was 14. And let's go with, let's go with 150, so 0.15 kilograms here. Let's do 150 on here. Oh, I need to get a starting spot. Well, we'll get an ending. Yeah, we'll get a starting spot on this. Well, let's calculate what we should get. All right, so how much force is acting right now on the green, or will be acting on the green?
1.47.
How much?
1.47.
Newtons?
Mm-hmm.
All right, so divide by the spring constant. When I put 150 grams on there, how much stretch should we expect?
8.4.
Centimeters.
Yeah.
8 centimeters, all right? 8.4 centimeters. All right, let's get a starting measure here. And starting measure 39.7. Ending measure 46. What's the actual stretch?
6.3.
Okay, so that came off just a little bit different. So there is a point at which the proportionality will not stay true. I wonder if we exceeded that with the 200 grams. I don't know. It's an interesting thought, though. And we'll talk more about that in our lesson tomorrow. Let's go to the lightweight spring now. What was its spring constant?
6.47.
What was it?
6.47.
6.47, all right. And how much mass? Now, we can't put too much or we could break the spring or permanently deform it. How much mass do we want to put on the spring? I can go, well, we're not going to do the 1,000. I think 500 might be too much. Somewhere between 50 and 500.
0.25.
250?
Yeah.
All right, so let's do 0.25. So we got a 200 and a 50. And to calculate the stretch we should expect.
37.8 centimeters.
So 0.25 times 9.8.
Oh.
And then divide the 6.47.
Yeah.
And we get,
37.9 when rounded.
so about 38 centimeters of stretch. We'll find out if this breaks it. All right, 250 is what we're putting on here. Oh, let me measure starting spot so we can remember it as it was. 20.3. And don't break. It's kind of bouncing a little bit here, but I'm going to say 58.2. What's the actual stretch we use?
37.9.
Yeah.
Wow. All right. Okay. Well, the good news is we didn't go past the proportional limit, so we didn't damage the spring. All right. Let's go to the tan rubber band here. This was the strongest of all of them, right? So I can load this thing up. Let's see here. What was its spring constant?
65.3.
65.3. And let's go 500. Let's go a half a Newton or half a kilogram on here. All right, figure out how much we should get stretched.
4.9.
How much?
7.5 centimeters.
Yeah.
Only 7.5 centimeters, really?
Yeah.
Wow, okay. I might put more.
Just do the 1,000.
I don't want to break it. I like good rubber bands. Okay, so this 32.7. That's not much at all. Okay, and yeah, 44, 45. Let's say 45. I feel like this hits its proportional. The rubber bands are hitting their proportional limit way too quickly.
12.3.
Yeah, way off, right? So, yeah, I'm feeling like the proportion on the rubber bands doesn't hold up as well, which again, we'll talk about proportional limit tomorrow, but that's an observation we're making, right? Whatever the rubber bands are made out of, they pass proportional limit rapidly. But okay, that gives us something to observe in our next lesson. All right, then we'll go to the medium spring. Its spring constant was
14.
Oh, that's right, that one came out evenly. And should we just leave the same 0.5 on there?
Yes.
I think you can probably handle it. Hopefully. So what stretch are we looking at?
35.
35 centimeters.
Mhm.
Okay, let's see what happens. All right, starting position 21.8. Ending position, it's bouncing, hold me still. 56.5.
34.7.
Okay, within just a few. Okay, so the springs themselves, the metal coiled springs, they seem to consistently follow Hooke's law. The rubber bands, Hooke's law seems to be fading. And you'll notice the book does point out for small deformations, the Hooke's law holds true. Obviously, there is a point at which, and you read this in your homework reading, the proportion ceases to happen, and elongation or deformation happens more rapidly, and that's what we're seeing with the rubber bands. The important thing is that we don't pass what's called the elastic limit, but we'll talk more about that tomorrow. All right, you're going to do a couple problems, page 79 now. Page 79, and I want you to do number 1, page 79, do problem number 1, and it's kind of doing the same thing, you just don't get the visual aspect, but working the same type of problems as what we were just doing. It's just written out like you would see it on a quiz or test. If you finish early, go on to problem 2, we're going to look at that one next. Let's still work on number 1. All right, go ahead and read problem number 1 for us, if you would, Kendall.
A 1.50 kilogram mass is held in a vertical spring with K equals 30.0 newtons per meter. What is the magnitude and direction of the tensile force acting on the spring, and how far did the spring stretch in meters and centimeters?
All right, so we're given some numbers first of all. We're given the mass is 1.5 kilograms, and we're given the spring constant is 30.0 newtons per meter, so a little stronger than this spring here. Remember, this was 27, so a little bit thicker and stronger than that spring. And it said, what's the magnitude and direction of the tensile force? Well, what is causing, if I hung 1.5 kilograms, don't break. Let's not do that. If I hung 1.5 kilograms, here's both these. Yeah, it's about 3 pounds, a little over 3 pounds there. So that's a fair bit of weight, right? As I'm really uncomfortably close to the camera for poor YouTube viewers. All right. So yeah, I mean that's a lot to be putting on that little guy. So we won't do that. We'll just work a problem about it and say it doesn't break in the problem because we like physics problems to work out great. But what is causing the tensile force? It's what you just felt in your hand. It's the weight, right? So the tensile force is mass times gravity because it is weight. And so when it says what's the magnitude and direction of the tensile force, all you had to do is take the mass times gravity. What was the tensile force here, Kendall?
45.
The mass times gravity. Right? Tensile force is weight, so tensile force in this case is mass times gravity.
Oh, 14.7.
Good, 14.7 newtons of tensile force. How many found that to be the tensile force? It's just the weight. Then it says, by the way, it says magnitude and direction. Well, what would be the direction of the tensile force? What direction does it act? Downward. What force acts upward? Restorative force, remember? So if we did, and we did it a moment ago, right? We put this on this spring, there's 1,000 grams, there's a kilogram, about 2.2 pounds of force pulling down. Well, there's also 2.2 pounds lifting up. If it weren't, then it would just still be stretching, right? The fact that it stopped here, what we call equilibrium, means the downward force and the upward force match. So yeah, the restorative force would be the opposite, negative 14.7 newtons, we could say. And then it says, how far would the spring stretch? Well, once I know these two, using Hooke's law, I can find the stretch, right? Stretch is going to be, divide away the k, f sub t over k. So we take the 14.7 divided by the 30. How far would we expect the spring to stretch, class?
0.49 centimeters or meters.
0.49 meters, which would be
49 centimeters.
49 centimeters, which, do I even have 49 centimeters it can stretch? I do. No, it's not as strong, so it would stretch a little further. I don't know. I'm going to do it. I hope I don't break the spring. Otherwise, Kendall will have to buy me a new spring.
Yeah, it's going to fall.
If it goes snap and puts my eye out, that would be unfortunate. All right, it could hold it, and it stretched. It's down to about the 79. It had been around the 20-something, so it stretched about 50 to 60. A little bit more than that one did because it's a little bit lighter spring. But there we go. Questions on number 1. All right, take a look at number 2. Read that for us if you would, Michael.
Find the magnitude and direction of a spring's restorative force on an object that is attached to a string with a constant of 250 newtons per meters and compressed at 6 centimeters.
Now this time the spring is compressed. If you look at these springs, you can't really compress them, right? They're already sprung tightly together. But a pen spring, okay, be honest. How many of you, when you were little, you would shoot the top of the pen across the room with the... He still does that. He never grew up. Okay. So anyway, you're like, we did when we were younger. All right, but you shoot the pen across the room, right? Well, that spring is already sprung out, right? So you can compress it in. So if you compress it inward, what direction does the restorative force act? Outward. And that's why as you compress it in, when you release, it shoots back outward, correct? And hence the spring can shoot things. So we're compressing it inward now, 6 centimeters, And the spring constant, 250 newtons per meter. This is a massive spring. How many ever looked at the spring at the top of a garage door before? You know, so there's that spring up there to keep it from overshooting. I'm picturing something like that, okay? Massively heavy-duty spring. And it's sprung out, apparently, as opposed to the coiled one, which is actually at the top of a garage door, but something that strong, and you somehow squish it in 6 centimeters. The question is, how much force would it take to do that? Think about this. What do we call the force that stretches? Tensile force. Do you realize that the opposite of stretching, don't break, would be compressing? And see, that's what I was going to would be compressing, right? How would I show that instead of stretching, I'm going the opposite direction? Negative. So here, compression force equals negative kx, and the restorative force would be kx. Does that make sense? Tensile force is kx, compression would be negative kx, in which case the restorative force acts back outward, which is the negative of the negative, which becomes positive. Did it ask about restorative force? Yes, it did. It asked about the restorative force. So in this case, we're going to go with the plain old k and the plain old x. Make sense? All right, so we're looking for the restorative force, and we know the spring constant, 250 newtons per meter, and the stretch is
6 centimeters.
the negative 6, right? That's where the negative comes from. But in our case, we'll just say 6 centimeters because the restorative force is strong enough to push back out those 6 centimeters, correct? All right, so 6 times 250 newtons per meter. Oh, centimeters though, right? So what do we have to do? Change that to meters. 0.06 meters. And notice the per meter and the meter will cancel. And we multiply 250 times 0.06, we get 15 newtons. All right, so we take 15 newtons of force to push that spring in 6 centimeters. Questions on Hooke's law. Now here's the thing that's frustrating about Hooke's law. I have 3 springs up here. They're all made of the same material. And yet every single one has a different K. Does that make sense? The reason they all have a different K is because one, the coils are very thin. The next, the coils are thicker. And the last, the coils are thicker still. The individual actual coil is thicker. If only there were a way to account for the thickness, then I could have a single constant for all of them. Does that make sense? Because they're all made of the same stuff. In theory, these probably are made of similar substance. Obviously, no, they're different colors, but I think the substance in them is the same. Well, they're different thicknesses, right? But if they had the same thickness, or if I could account for the thickness in some way, I could have a single constant for them if I found a way to account for the thickness. Because right now, the spring constant is accounting for it, right? It's both accounting for what's it made out of and how thick is it. But what if I could account for both? That's where instead of talking about force, we want to talk about force based on compared to thickness, or force per unit area. Sound familiar? What do we call force per unit area? Pressure. But when we talk about force per unit cross-sectional area causing deformation, we change the name and we call it stress. Stress. Stress is defined as deformative force per unit area. Stress is defined as deformative force per unit cross-sectional area. Deformative force per unit cross-sectional area. So stress can be thought of as pressure, but specifically that which causes deformation. Oftentimes students tell me, I'm so stressed because of exams. I'm like, are you deforming? You look fine. Okay? You might feel like you're under pressure. I mean, we could debate the force per unit area on that, but you're certainly not under stress if no deformation is happening. Now, part of your brain starts caving in. Now we can talk about stress, but okay, I'm just kidding. Totally different type of stress, right? Non-physicsy stress, right? But stress is defined as deformative force per unit cross-sectional area. And if I can account for the cross-sectional area, that allows me to just look at, okay, what's it made out of? But there's another issue, right? Because the other thing is, that which is already long, like imagine another rubber band like this, and I don't have one of this same thickness, but imagine one that's only this big, okay? As opposed to this one. This one, if I stretch it this far, nobody's shocked, because it was already bigger than that. But imagine if I took a rubber band that big and tried to stretch it that same distance. It would probably snap, right? Because it's not so much just the amount of stretch that we're interested in, but the amount of stretch compared to how big something was to begin with, right? For instance, if Michael grew 1 inch, you guys might not notice. If Kendall grew 1 inch, that's a bigger deal, right? Okay, seriously though, if my son, who's only this tall, grows 1 inch, he's going to have growing pains as his bones, muscles, everything begins to elongate. At my height, if I grew 1 inch, that would be really cool at my age. But if I grew 1 inch, I might not notice the same pain. Why? Because relative to my height, my stretch or my change in length doesn't really make a big difference. Does that make sense? Take something that's this big and try to stretch it 3 inches. Wow. Take something this big and stretch it 3 inches. You barely notice. Does that make sense? So the other thing is, it's not so much about the stretch as much as it is the stretch compared to how long the thing was. Because that also makes a difference, right, in the spring constant. But if I can account for the deformation relative to the original size, now I can come up with this substance has this constant. Relative deformation is called strain. Strain. Strain is relative deformation. The amount of deformation compared to how big the original thing was. Or, like I say, relative deformation. As we deal with the idea of stressing something with tensile stress or applying a tensile force, that's found by saying the change in length over the original length. Change in length over original length. Delta L, delta, I think, have we seen that yet this year? Delta meaning change. I don't think that's been this year. I think maybe last year in chemistry you saw it though. This symbol delta, you'll see it throughout the year quite often, simply means change. So delta L means change in length, and then L sub O refers to the original length. And just as force and stretch are proportional, stress and strain are proportional as well. But instead of using a generic letter K to represent a constant of proportionality, stress and strain, or shall I say tensile stress, stretching or compressing stress, stretching positive, compressing negative, and strain are proportional as well. But every substance, not every object, but every substance has its own proportionality constant. Anything made of steel has the same proportionality constant. Anything made of latex has the same proportionality constant. All muscle fiber, well, okay, assuming average muscle density and composition, has the same proportionality constant. And now you can suddenly construct a table of values that can be useful. We call the proportionality constant Young's modulus, after Thomas Young, who broke the ground on this. Young's modulus of deformation, or just Young's modulus. This proportionality number is based on the amount of strain needed, or the amount of stress needed, rather, to produce a doubling in length. Okay, but Young's modulus, you just need to know that's the proportionality constant. We'll represent it with the letter Y. Young's modulus is the proportionality constant for tensile stress. So since stress and strain are proportional, just as force and stretch were proportional, we could say that F over A, stress, equals the proportionality constant, just like K, but now it's Y, times not stretch, but strain. Change in length over original length. And here's the next equation you need to know for this chapter. F over A equals Y times delta L over L sub O. Stress proportional to strain. I will say this, though. As we go throughout the chapter, most of the time, you're going to be trying to figure out what the change in length is. We'll usually be, just the way the problems work out, we'll usually be given how much force is applied, the cross-sectional area, or maybe a diameter, for instance, which is not analogous to d squared here because we don't have an area on the other side. The original length, Young's modulus, you could look up on the internet. We have a table of commonly used values. Usually we'll be looking for the delta L. So if I wanted to get the delta L by itself, how would I get rid of the L sub O? Multiply, which puts it up here in the top, right? Because when you multiply, it goes to the numerator. How would I get rid of the Y? You would divide it because it's being multiplied, which will put it down in the denominator. So the way we usually use the equation is delta L equals force times original length over cross-sectional area times Young's modulus. This is the way we'll use it more often than not. And the nice thing about the other way is you just remember what stress is by definition, strain is by definition, and then you're put instead of K a Y, and you're in good shape. This is easy to remember. How many have seen the Progressive commercials? Right? Who's the heroine of the Progressive commercials? Flo. Now, be honest with me, okay? You may or may not like the Progressive. How many like the Progressive commercials? They're good. How many like, no, Geico does them better? Okay? Regardless, though, if you were like walking downtown Columbus and you happened to see Flo on the street, that would still be pretty cool, right? You're like, hey, Flo, hey, Flo, hey. Now it's dumb, but if it helps you remember how to find change in length or elongation, deformation, then more power to you. But this is generally how we'll use the equation, is flow over A. Force times change in original length over cross-sectional area times Young's modulus. Look in your books if you would, page 73. Page 73 in your textbooks. And look at the first example problem. It says, find the elongation of a 5 centimeter long tendon with a diameter of 0.4 centimeters if it's subjected to a force of 1,470 newtons. All right, so notice what they did first. They found the cross-sectional area. Remember, cross-sectional area, if it's circular cross-section, is going to be pi r squared. So they had to cut the diameter of 0.4 centimeters and have to get 0.2 centimeters, but then they had to change it to meters, 0.002 meters, and that 2 meters, and that gets squared times pi, and that gave them their area that you see there. So they just plugged in their numbers. They had their force of 1,470 newtons, they had their original length, stay with me, of 5 centimeters, their cross-sectional area, which was that crazy looking number they found, and then the Young's modulus. That's on this table here. Notice there's 3 columns, but all we care about right now is the y, okay, the Young's modulus. And notice that a tendon has a Young's modulus of 0.5, what? Well, look at the top of the chart. See where it says moduli for very solid materials times 10 to the 10th pascals? The tendon's Young's modulus is 0.5 E10 pascals. So that's what they plugged in here, 0.5 E10 pascals, or newtons per meter squared, which is a pascal. Plugged in the numbers, and I'm getting 1.2 E negative 3 meters. Unfortunately, we're out of time, so I didn't give you a chance to practice it. You will practice it with homework, and do your best. We'll go over it tomorrow, so if you're like, just do your best, think it through, plug in the numbers, try your hardest. We'll take a look at this tomorrow, but obviously did not get as far as I wanted to today. Page 79. Page 79. I want you to do problems 3A, and I think we might just do 2. We might do 3A and 5A. Let's do that. Problems 3A and 5A. Okay, so page 79, problems 3A and 5A. We'll look more at this in our next lesson. Have a wonderful rest of your day, and you are dismissed.